inside every proton in your body, something impossible is happening. Particles called gluons are flying back and forth, carrying the strongest force in the universe. A force so powerful, it makes electromagnetism look feeble. These gluons are real, they carry energy, they have measurable effects, and yet, no one has ever seen one alone. No experiment has ever isolated a single gluon. Not because our technology isn't good enough, but because the universe literally won't allow it. If you try to pull a gluon out of a proton, something extraordinary happens. The harder you pull, the stronger the force pulls back. And if you pull hard enough, instead of freeing the gluon, you create entirely new particles from nothing. The gluon never escapes. It's a prisoner of its own force. And the reason why reveals one of the strangest truths in all of physics. If you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing, but it means a lot. Now, let's begin. Let's start with something you already know, but probably haven't thought deeply about. You're made of atoms. Everything around you is made of atoms. The chair you're sitting in, the screen you're looking at, the air you're breathing, your own body. Atoms are the building blocks of all ordinary matter in the universe, and at the center of every atom is a nucleus, a tight little knot of particles called protons and neutrons, bound together in an almost impossibly small space. The nucleus of an atom is tiny. If an atom were the size of a football stadium, the nucleus would be about the size of a marble sitting at the center of the field. Everything else would be empty space, with electrons buzzing around in the stands. That marble at center field contains almost all the atom's mass. Over 99.9% of the mass of every atom is locked inside that minuscule nucleus. And here is where things get strange. Here is where a problem appears that most people never think about. A problem so severe that it threatened to destroy our understanding of physics for decades. Consider a helium nucleus. It contains 2 protons and 2 neutrons. Focus on the protons. Each proton carries a positive electric charge, and one of the most fundamental rules of electromagnetism, a rule you learned in school, is that like charges repel. Positive pushes away from positive, negative pushes away from negative. Only opposite charges attract. So 2 protons sitting next to each other inside a helium nucleus should be pushing apart with enormous force. And they are. The electromagnetic repulsion between 2 protons inside a nucleus is staggering. At the distances we're talking about, roughly 1 femtometer, which is 1 quadrillionth of a meter, the electromagnetic force pushing those protons apart is about 230 newtons. That might not sound like much, until you realize we're talking about 2 particles so small that 100 trillion of them could fit across the width of a human hair. At that scale, 230 newtons is a colossal force. It should blast those protons apart instantly. The nucleus should explode the moment it forms. And yet it doesn't. Nuclei exist, they're stable. Some of them are extraordinarily stable. An iron 56 nucleus contains 26 protons all crammed together, all pushing apart with tremendous electromagnetic force, and it holds together for essentially forever. It's one of the most stable configurations of matter in the entire universe. Something is holding those protons together. Something is overpowering the electromagnetic repulsion and binding the nucleus into a tight, stable structure. That something is the strong force. And the strong force isn't just a little stronger than electromagnetism, it's dramatically, overwhelmingly stronger. At the distances relevant to the nucleus, the strong force is roughly 100 times more powerful than the electromagnetic force. It doesn't just barely win the tug of war, it dominates completely. Without the strong force, no nucleus heavier than hydrogen could exist. No helium, no carbon, no oxygen, no iron, no uranium. Chemistry as we know it would be impossible, because chemistry requires elements, and elements require nuclei, and nuclei require the strong force to hold them together. Without this force, the universe would contain nothing but isolated protons and neutrons drifting through empty space. No stars, no planets, no molecules, no life. Nothing. The strong force is the reason complex matter exists. It's the reason the periodic table has more than one entry. It's the reason you exist. And yet, for a long time, physicists didn't understand how it worked. They knew it was there. They could see its effects in the stability of nuclei, in the way nuclear reactions released enormous amounts of energy, in the behavior of particles in early accelerator experiments. But the underlying mechanism was a mystery. The breakthrough came in stages over several decades, and to understand it, We need to look deeper than the nucleus. We need to look inside the proton itself. For most of the 20th century, protons and neutrons were considered fundamental particles. They were thought to be indivisible, the smallest building blocks of nuclear matter. But experiments in the late 1960s changed everything. At the Stanford Linear Accelerator Center, physicists fired high-energy electrons at protons and observed something unexpected. The electrons were scattering off the protons in a pattern that didn't match a smooth, uniform particle. Instead, the scattering pattern looked like the electrons were bouncing off small, hard objects inside the proton. It was reminiscent of Ernest Rutherford's famous gold foil experiment from 1911, when alpha particles bouncing backward off gold atoms revealed the existence of the atomic nucleus. Now, decades later, a similar pattern was revealing that the proton itself had internal structure. There were smaller things inside it. These smaller things turned out to be quarks. The idea of quarks had already been proposed independently by two physicists, Murray Gell-Mann and George Zweig, in 1964. Both suggested that protons, neutrons, and other particles called hadrons were not fundamental, but were composed of more basic constituents. Gell-Mann called them quarks, borrowing the word from a passage in James Joyce's novel Finnegan's Wake. But the quark proposal didn't come out of nowhere. It came from desperation. By the early 1960s, particle physics was drowning in particles. Every time experimentalists built a more powerful accelerator and smashed protons or other particles together at higher energies, they discovered new particles. Not just a few, hundreds. The rho meson, the omega meson, the phi meson, the delta baryons, the sigma baryons, the xi baryons, the lambda, the eta, the kaons in multiple varieties. The list grew longer every year. Physicists called it the particle zoo, and the name captured the bewilderment they felt. In the early days of nuclear physics, the universe seemed simple. Protons, neutrons, electrons, and photons. 4 particles, clean, elegant. By the early 1960s, there were over 100 supposedly fundamental particles, with more being discovered every few months. It was chaos. Nobody believed nature could truly require this many fundamental building blocks. There had to be a deeper pattern, a simpler structure underneath. Several physicists tried to organize the chaos. Gell-Mann himself, along with Israeli physicist Yuval Ne'eman, independently discovered that the known hadrons could be arranged into geometric patterns based on their properties, their charge, their strangeness, their spin. These patterns, which Gell-Mann called the Eightfold Way, after a Buddhist concept, were mathematically elegant and highly predictive. The Eightfold Way organized hadrons into families the same way the periodic table organizes elements. And just as the periodic table's structure hinted at deeper atomic structure, the Eightfold Way's patterns hinted at deeper substructure inside hadrons. Gell-Mann's quark model explained why these patterns existed. If you built hadrons from combinations of 3 types of quarks, up, down, and strange, each with specific charges and masses, you could reproduce every pattern the Eightfold Way had revealed. Every known hadron was accounted for, and the model predicted particles that hadn't been seen yet. In 1962, Gell-Mann predicted the existence of the omega- baryon based on a gap in the Eightfold Way's patterns. It was discovered 2 years later at Brookhaven National Laboratory, with exactly the properties he had predicted. This was a stunning confirmation. The quark model brought order to chaos. All those hundreds of particles could be explained as different combinations of just a few types of quarks. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. Other, more exotic particles are made of different quark combinations. The model was elegant and powerful, but it also raised a serious question. If quarks are real particles inside protons, what holds them together? What force binds quarks into protons and neutrons? And why has no one ever seen a quark by itself, free and isolated, outside of a hadron? This is where the story takes a remarkable turn. The force that binds quarks together is the strong force, but not the strong force as it was originally understood at the nuclear level. Physicists realized that the strong force holding nuclei together was actually a residual effect, a kind of spillover from a more fundamental force operating at a deeper level. Think of it this way. The force between 2 atoms in a molecule is electromagnetic, but it's not the fundamental electromagnetic force between individual charges. It's a residual effect. The charges inside each atom are mostly balanced, but tiny imbalances create a weak residual force between neighbouring atoms. This residual force, the van der Waals force or chemical bonding, is much weaker than the fundamental electromagnetic force between bare charges. Something analogous happens with the strong force. The fundamental strong force operates between quarks inside a proton or neutron. It's immensely powerful. But each proton and neutron is color neutral, meaning its strong charges are internally balanced. The force between neighboring protons and neutrons in a nucleus is a residual spillover of this internal force, leaking out through small imbalances, much weaker than the fundamental quark-level interaction. So the nuclear force that holds protons and neutrons together in a nucleus is actually the faint echo of something far more powerful happening inside each proton and neutron. The fundamental strong force operates between quarks. It's carried by particles called gluons, and it's described by a theory called quantum chromodynamics, or QCD. This name deserves unpacking because it tells you a lot about what the theory describes. Quantum means the theory incorporates quantum mechanics. It deals with probabilities, wave functions, and the bizarre behavior of the subatomic world. Chromo comes from the Greek word for color, chromos. It refers to a property of quarks called color charge, which we'll explore in depth. And dynamics means the theory describes how things change and interact over time. Quantum chromodynamics, the quantum dynamics of color. Now, color charge has absolutely nothing to do with actual colors. Quarks aren't literally red or green or blue. You can't see them with your eyes. Color charge is a label physicists gave to a property of quarks that governs how they interact through the strong force. It's analogous to electric charge in electromagnetism. In electromagnetism, particles carry electric charge. Charge comes in two types, positive and negative. Opposite charges attract, like charges repel. The force is carried by photons, which are massless particles of light. Every electromagnetic interaction, from magnets sticking to your refrigerator to the light from your screen reaching your eyes, is mediated by photons traveling between charged particles. The strong force works on a similar principle, but with a crucial difference in complexity. Instead of two types of charge, positive and negative, the strong force has three types of charge. Physicists labeled them red, green, and blue, borrowing the names of the three primary colors of light. Every quark carries one of these three color charges. A quark can be red charged, green charged, or blue charged. And just as electric charge has an opposite, each color has an anti-color. There's anti-red, anti-green, and anti-blue. Antiquarks carry anti-color charges. This threefold structure of color charge is what makes the strong force so much richer and more complex than electromagnetism. In electromagnetism, you have two charges and one force carrier, the photon. In the strong force, you have three colors and three anticolors and 8 different types of force carriers. Those force carriers are gluons. 8 types of gluons, each carrying different combinations of color charge. We'll explore exactly what that means and why it has such extraordinary consequences shortly. But first, there's something fundamental to understand about how color charge works. The key principle of quantum chromodynamics is called color confinement, or sometimes just confinement. It states that only color-neutral particles can exist as free, independent objects. A color-neutral particle is one whose color charges cancel out, just as an electrically neutral atom has equal positive and negative charges that cancel. There are 2 ways to make a color-neutral combination. The first is to combine all 3 colors together. Red plus green plus blue equals color neutral, just as red plus green plus blue light combine to make white light. This is where the color analogy comes from. A particle made of 3 quarks, 1 red, 1 green, and 1 blue, is color neutral. This type of particle is called a baryon. Protons and neutrons are baryons. Every proton contains 3 quarks carrying red, green, and blue color charges respectively, combining to produce a color-neutral whole. The second way is to pair a color with its anti-color. Red plus anti-red is neutral. Green plus anti-green is neutral. Blue plus anti-blue is neutral. A particle made of 1 quark and 1 antiquark, with matching color and anti-color, is color-neutral. These particles are called mesons. Pions and kaons are examples of mesons. In either case, the rule is absolute. Only color-neutral combinations are ever observed in nature as free particles. You never see a lone red quark wandering through space. You never see a pair of quarks that together carry a net color charge. You never see a free gluon drifting through a detector. Every particle that exists freely in the universe is color-neutral. No exceptions have ever been found, despite decades of searching. This is deeply strange when you think about it. In electromagnetism, there's no such restriction. You can have a free electron sitting by itself carrying negative charge. You can have a free proton carrying positive charge. Charged particles exist independently all the time. But quarks and gluons can't do this. They are permanently confined inside color-neutral hadrons. They exist, they're real, they have measurable properties, but they can never be isolated. Now, you might wonder how we know quarks and gluons are real if we can never isolate them. This is a fair question and it's worth addressing. The evidence is overwhelming, but it's indirect. We know quarks are real because of the deep inelastic scattering experiments at Stanford that I mentioned earlier. When high-energy electrons are fired at protons, the pattern of scattering matches what you'd expect if the electrons were bouncing off point-like objects inside. The experiments measured the charges, spins, and momenta of these internal constituents, and everything matched the quark model's predictions precisely. We know gluons are real because of experiments at particle accelerators, particularly at the electron-positron collider called Petra at the DESI laboratory in Hamburg, Germany. In 1979, physicists at Petra observed something remarkable. When electrons and positrons annihilated each other at high energies, they sometimes produced 3 distinct jets of particles spraying outward. 2 of the jets were expected. They corresponded to a quark and an antiquark being created from the collision energy, each one generating a spray of hadrons as it tried to fly away and was confined. But the 3rd jet was something new. It corresponded to a gluon being radiated by one of the quarks, a gluon carrying enough energy to produce its own separate spray of hadrons. This was the first direct experimental evidence for the existence of gluons. Since then, gluon evidence has only grown stronger. Experiments at the Large Hadron Collider and other facilities have mapped out the gluon distribution inside protons with extraordinary precision. We know how many gluons are inside a proton at any given moment, how they share the proton's momentum, how they interact with each other. The picture is detailed and well confirmed, so quarks and gluons are unquestionably real, but they're also unquestionably confined. And understanding why they're confined requires understanding something unique about gluons, something that sets them apart from every other force carrier in physics. In electromagnetism, the force is carried by photons. Photons are electrically neutral. They carry no electric charge. This is important. It means photons don't interact with each other through electromagnetism. 2 photons can pass right through each other without affecting one another. Light beams cross in mid-air without deflecting or scattering. Flashlights don't push each other's beams aside. Photons are blind to each other because they don't carry the charge of the force they transmit. This makes electromagnetism relatively simple. The force between 2 charged particles is carried by photons traveling back and forth. The photons themselves don't generate additional electromagnetic fields because they're neutral. The interaction is clean, straightforward, and well-behaved. The force weakens smoothly with distance, falling off as the square of the distance, just as Newton described for gravity. At larger separations, the electromagnetic force between 2 charges fades and eventually becomes negligible. Gluons are profoundly different. Gluons carry color charge. They are not neutral with respect to the force they transmit. Each of the 8 types of gluons carries a combination of one color and one anticolor. A gluon might carry red and anti-blue, or green and anti-red, or some more complex combination. The precise details of these combinations involve group theory, a branch of mathematics dealing with symmetry, and the specific symmetry group of the strong force is called SU3. The 8 gluon types correspond to the 8 generators of this symmetry group, but the mathematical details aren't what matter here. What matters is the physical consequence. Because gluons carry color charge, they interact with each other through the strong force. A gluon can emit or absorb another gluon. Gluons attract each other. Gluons can form temporary bound states with other gluons. The force carriers themselves are sources of the force. This is like nothing in electromagnetism. Imagine if photons were electrically charged. They'd interact with each other. Light beams would push and pull on each other. The electromagnetic field around a charged particle would itself generate more electromagnetic field. The whole structure of electromagnetism would change dramatically. It would become nonlinear, self-interacting, far more complex, and far more difficult to calculate. That's essentially what happens with the strong force. The gluon field is self-interacting. Gluons don't just transmit the force between quarks, they also interact among themselves, creating a web of force that behaves in ways electromagnetism never does. This self-interaction is the single most important feature of quantum chromodynamics. It's what makes the strong force behave so differently from electromagnetism. It's what causes confinement. It's the reason quarks and gluons can never be isolated. And it's the reason the gluon cannot exist as a free particle. Everything about the strong force that seems strange and counterintuitive, the impossibility of isolating quarks, the permanent confinement of color charge, the bizarre behavior of the force at different distances, all of it traces back to this one fact. Gluons carry color charge. The force carrier is charged under its own force. To understand what this means in practice, think about what happens when you place two quarks near each other. They exchange gluons, just as two electrons exchange photons. But those gluons, carrying color charge, interact with each other along the way. They pull on each other, they attract. And as a result, the color field between two quarks doesn't spread out in all directions like an electric field does. Instead, it gets squeezed. It collapses into a narrow tube, a string-like structure of concentrated gluon field stretching between the two quarks. This tube is called a flux tube, or sometimes a color string. It's a direct physical consequence of gluon self-interaction. In electromagnetism, the field lines between two charges spread out into space, fanning outward like the bristles of a brush. The farther apart the charges, the more the field spreads and the weaker the force becomes. The force drops as the square of the distance. Double the separation and the force drops to 1/4. But in the strong force, the field lines don't spread. The gluons pulling on each other keep the field compressed into that narrow tube, and the energy stored in the tube is proportional to its length. Pull the quarks farther apart and the tube gets longer. The energy increases. The force doesn't weaken. In fact, it stays roughly constant regardless of distance. This is completely unlike any everyday force. Every force you've ever experienced in your daily life weakens with distance. Gravity weakens. Electromagnetism weakens. Even a stretched rubber band, though it resists more as you pull, will eventually snap. But the color force between quarks doesn't weaken, and the flux tube doesn't snap in the way you might expect. Instead, something far stranger happens, something we'll explore in detail later. For now, the essential point is this. The strong force is carried by gluons. Gluons are fundamentally different from photons because they carry color charge. This color charge means gluons interact with themselves, creating a self-reinforcing field that doesn't spread out or weaken over distance. This self-interaction is the engine behind the most distinctive feature of the strong force, the feature that defines its identity and shapes the structure of all matter in the universe. Confinement. The permanent imprisonment of quarks and gluons inside hadrons. No parole, no escape, no exceptions. And it all starts with the fact that the messenger itself is entangled with the message. The carrier of the force is subject to the very force it carries. This makes the strong force unique among all four fundamental forces of nature. Gravity is carried by gravitons, which in principle carry energy and therefore interact gravitationally. But the effect is so weak it's never been measured, and gravitons themselves haven't been directly observed. The weak force is carried by W and Z bosons, which do carry weak charge and interact with each other, but the weak force has an extremely short range because W and Z bosons are massive. They weigh about 80 to nearly 100 times the mass of a proton, which limits their reach to roughly 1/1000th of a femtometer. The weak force's self-interaction is real, but plays out over such tiny distances that confinement doesn't occur. Electromagnetism's photons are neutral, and don't self-interact at all at tree level, as physicists say, meaning the simplest interactions don't involve photon-photon coupling. There are extremely tiny quantum corrections where photons can interact indirectly through virtual electron-positron pairs, but these effects are negligibly small in almost all circumstances. The strong force is the only one where the self-interaction of the force carrier is powerful, dominant, and has dramatic physical consequences, observable in every proton and neutron in the universe. 8 types of gluons, each carrying combinations of color and anticolor, constantly being exchanged between quarks, constantly interacting with each other, constantly reinforcing the confining field. Inside every proton in your body right now, this process is happening. Gluons are flying between quarks, emitting and absorbing other gluons, creating a roiling, dynamic web of color force that holds the quark trio together. The interior of a proton is not a calm, orderly place. It's a seething storm of quantum activity. Gluons outnumber quarks inside a proton by a significant margin. At any given instant, there are far more gluons than quarks in there, along with a constantly churning sea of virtual quark-antiquark pairs popping in and out of existence. The proton is less like 3 billiard balls connected by springs, and more like three boats caught in a violent ocean, an ocean made entirely of gluons. And every single one of those gluons is trapped. Just like the quarks, no gluon can escape the proton's boundary because every gluon carries color charge, and color charge cannot exist freely. The very property that allows gluons to do their job, carrying the strong force, is the same property that imprisons them. They are simultaneously the jailers and the prisoners, the guards locked inside their own prison. This is the deep paradox at the heart of the gluon's existence. It's a particle defined by a force it can transmit, but can never escape. It exists everywhere inside ordinary matter, playing a role more important than most people realize, contributing to the mass of every atom, holding the fabric of the physical world together. And yet it is permanently, fundamentally, inescapably hidden from direct observation. You will never hold a gluon. You will never detect one flying freely through space. You will never isolate one in any laboratory, no matter how advanced. The universe simply won't allow it. And the reason, the deep physical reason, is that the gluon carries every moment of your waking life. That single fact, every time you see anything at all, reshapes everything about how the strong force signals in your retina and creates a physical reality. Every time you feel unlike anything else in nature, photons are delivering energy to your skin. Color charge matters so photons are the carriers of the electromagnetic force carriers work in physics. They're responsible for virtually every gluon isn't just unusual. It's light, fundamentally unique. Radio particles that carry the four known forces, the repulsion between like charges, and that uniqueness has consequences that ripple through every structure of existence. The behavior of magnets. Let's start with the most familiar force carrier through fiber optic cables. You interact with photons as photons doing their work. Now here's the key point about photons. A photon has no electric charge, zero. It's completely electrically neutral. When a photon travels between two electrons, mediating the electromagnetic force between them, the photon itself doesn't feel that force. It's carrying a message about electric charge, but it doesn't have any of its own. It's like a mail carrier delivering letters about a subject they have no personal connection to. The mail carrier picks up the letter, carries it to the destination, and drops it off. The content of the letter doesn't affect the carrier. The carrier doesn't interact with other carriers based on the content of the letters they're holding. Each carrier does its job independently, oblivious to the others. This is why electromagnetism is what physicists call an abelian gauge theory. The word abelian, named after Norwegian mathematician Niels Henrik Abel, refers to a mathematical property of the symmetry group underlying electromagnetism. In abelian theories, the order in which you perform symmetry operations doesn't matter. More practically, it means the force carriers don't interact with each other through the force they carry. Photons don't push or pull on other photons electromagnetically. They just pass through each other, each one independently carrying out its role of mediating the force between charged particles. This makes electromagnetism elegant and mathematically tractable. The equations are linear, meaning the fields produced by multiple charges simply add together. If you have two charges, you calculate the field from each one separately and add the results. The field from charge A doesn't interact with the field from charge B, they just coexist, superimposed on top of each other. This superposition principle is one of the most powerful tools in electromagnetic theory. It makes calculations manageable. It's why we can predict the behavior of electromagnetic systems with extraordinary precision. The strong force doesn't work this way, not even close. Quantum chromodynamics is a non-abelian gauge theory. The symmetry group underlying the strong force is called SU3, a group from a branch of mathematics called Lie group theory. In non-abelian theories, the order of symmetry operations does matter. The mathematical structure is richer, more complex, and more demanding, and the physical consequence that matters most is this. The force carriers interact with each other through the very force they carry. Gluons carry color charge. Each gluon carries a combination of one color and one anti-color. A gluon might carry, for instance, red color charge and anti-blue color charge simultaneously. Another gluon might carry blue and anti-green. Another might carry green and anti-red. The exact combinations are determined by the mathematics of SU3, and there are 8 independent types of gluons, corresponding to 8 generators of the symmetry group. Why 8? You might expect 9, since there are 3 colors and 3 anti-colors, giving 9 possible color and anti-color pairings. And indeed, you can write down 9 combinations. Red anti-red, red anti-green, red anti-blue, green anti-red, green anti-green, green anti-blue, blue anti-red, blue anti-green, and blue anti-blue. But one particular combination of the 3 color and anti-color diagonal states, the combination that would be red anti-red plus green anti-green plus blue anti-blue in equal proportion, is actually color neutral. It carries no net color charge. It would behave like a color singlet, unable to interact through the strong force. Nature doesn't use it as a gluon, so you're left with 8 gluons, not 9. These 8 gluons are the workhorses of the strong force. They're constantly being exchanged between quarks inside every proton and neutron. But because each gluon carries color charge, something happens that has no parallel in electromagnetism. When a gluon travels between 2 quarks, it can emit another gluon along the way, or absorb one, or interact with gluons emitted by other quarks. The field generated by the gluons generates more field. The force carriers are themselves sources of the force. Think about what this means in concrete physical terms. In electromagnetism, the field between 2 charges is generated only by those charges. The photons carrying the force don't add to the field. They are the field in a quantum sense, but they don't create additional field on top of what the charges produce. The situation is clean. 2 charges produce a field. The field acts on charges. That's it. In the strong force, the quarks produce a color field by exchanging gluons, but those gluons, carrying color charge, also produce color field, and that additional field is carried by more gluons, which produce more field, which is carried by more gluons. It's recursive, self-reinforcing. The field feeds on itself. Each layer of gluons generates another layer. The result is a field that behaves in a fundamentally non-linear way, where doubling the charge doesn't simply double the field. The whole system is tangled together in a way that makes it far more complex and far more powerful than electromagnetism. This is not just a theoretical curiosity. It has direct, measurable physical consequences that change the behavior of the strong force in ways that are genuinely shocking when you first encounter them. Consider what happens with electromagnetism over distance. Place 2 electrically charged particles near each other. They feel a strong force. Now pull them apart. The force weakens. It follows an inverse square law. Double the distance and the force drops to 1/4. Triple it and the force drops to 1/9. At large separations, the electromagnetic force between 2 charges becomes negligible. This is familiar and intuitive. Things that are far apart don't push or pull on each other very strongly. The reason this happens is that the electric field lines spread out in all directions from a charge. As you move farther from the charge, those field lines are distributed over a larger and larger area, like the surface of an expanding sphere. The field strength at any given point decreases because the same total flux is spread over more space. This is basic geometry, and it gives electromagnetism its characteristic distance behavior. But there's another effect happening at the quantum level that makes the force weaken even faster at short distances, or more precisely, that makes it effectively stronger at short distances than you'd naively expect from the inverse square law alone. This effect is called vacuum polarization, or charge screening. In quantum electrodynamics, the vacuum isn't empty. It's filled with virtual particle-antiparticle pairs, electrons and positrons, constantly appearing and disappearing. These virtual pairs are not real particles in the conventional sense. They exist for incredibly brief moments, allowed by the uncertainty principle, before annihilating back into nothing. But during their brief existence, they respond to nearby electric charges. If you place a positive charge in the vacuum, the virtual electron-positron pairs orient themselves around it. The virtual electrons, being negatively charged, are pulled slightly toward the positive charge. The virtual positrons are pushed slightly away. This creates a cloud of virtual negative charge surrounding the real positive charge, partially cancelling it. The farther away you look, the more virtual pairs are between you and the real charge, and the more the charge appears to be reduced. This is screening. The effective charge you see from a distance is smaller than the bare charge at the centre. The consequence is that as you get closer to a charged particle, pushing through the screening cloud, the effective charge appears to increase. At very short distances, you see more of the true unscreened charge. The coupling between charges appears stronger at short range and weaker at long range. In quantum electrodynamics, the effective coupling constant, a number that measures the strength of electromagnetic interactions, slowly increases at shorter distances and higher energies. This increase is tiny and gradual. At the energies accessible in laboratory experiments, the electromagnetic coupling constant changes from about 1/137 at low energies to about 1/128 at the energies achieved in the Large Electron-Positron Collider. A small shift, but a real and measured one. Now let's look at what happens in the strong force, and this is where the gluon's color charge creates something truly extraordinary. In quantum chromodynamics, the vacuum is also filled with virtual particles. Virtual quark-antiquark pairs appear and disappear, just as virtual electron-positron pairs do in electromagnetism. And these virtual quark pairs do screen the color charge of a real quark, just as virtual electron-positron pairs screen electric charge. If this were the only effect, the strong force would behave similarly to electromagnetism. The effective color charge would increase at shorter distances and decrease at longer distances. Screening would make the strong force weaker up close and stronger far away. But this is not the only effect. There is something else happening in QCD that doesn't happen in electromagnetism. The gluons themselves carry color charge, and virtual gluons in the vacuum behave very differently from virtual quark pairs. Instead of screening the color charge, virtual gluons do the opposite. They anti-screen it. When a quark sits in the QCD vacuum, virtual gluon fluctuations surround it. But because gluons carry color charge, their effect on the surrounding field is not to cancel the quark's charge, but to spread it out, to amplify it at a distance. The virtual gluon cloud actually makes the color charge appear stronger at larger distances and weaker at shorter distances. This is the opposite of what virtual quarks do. It's the opposite of what happens in electromagnetism. And here's the critical point. In QCD, the anti-screening effect from virtual gluons is larger than the screening effect from virtual quarks. The gluon contribution wins, not by a little, but by a significant margin. There are 8 types of gluons all contributing to anti-screening, and their collective effect overwhelms the screening from quarks. The net result is that the effective strong coupling constant decreases at shorter distances and increases at longer distances. The strong force gets weaker when quarks are close together and stronger when they're far apart. This behavior is called asymptotic freedom. At asymptotically short distances, quarks behave almost as if they were free particles, barely interacting. But as the distance between them increases, the force grows. The quarks are increasingly bound. They become less and less free. Eventually, the coupling becomes so strong that perturbative calculations, the standard mathematical technique for handling quantum field theories, break down entirely. The force is too strong for the usual approximation methods. Asymptotic freedom was discovered in 1973 by David Gross, Frank Wilczek, and David Politzer. Gross and Wilczek were at Princeton University. Politzer was at Harvard. Working independently, they calculated the behavior of the strong coupling constant as a function of energy scale and discovered that it decreased at higher energies, corresponding to shorter distances. This was unexpected. Most physicists assumed all quantum field theories would behave like electromagnetism, with couplings increasing at higher energies. The discovery that the strong force runs in the opposite direction was a revelation. The calculation required understanding the contributions of both virtual quarks and virtual gluons to the effective coupling. The quark contribution pushed the coupling higher at shorter distances, just as in electromagnetism. But the gluon contribution, the new ingredient unique to non-abelian gauge theories, pushed the coupling lower, and the gluon contribution was dominant. The net effect was a coupling that weakened at short range and strengthened at long range. This discovery earned Gross, Wilczek, and Politzer the Nobel Prize in Physics in 2004. The Nobel Committee cited them for the discovery of asymptotic freedom in the theory of the strong interaction. It was recognized as one of the most important theoretical discoveries in particle physics because it provided the foundation for understanding QCD as the correct theory of the strong force. Asymptotic freedom explains why the deep inelastic scattering experiments at Stanford worked the way they did. When high-energy electrons probe the inside of a proton, they're probing at very short distances. At those distances, the strong coupling is weak. The quarks inside the proton are barely interacting with each other. They behave almost like free particles. This is why the scattering pattern matched point-like, nearly free quarks. The electrons were seeing quarks in the asymptotically free regime, where the strong force is gentle. But this gentleness is an illusion of proximity. Step back just a little, increase the distance between quarks by even a tiny amount in subatomic terms, and the force begins to reassert itself. Pull a quark farther from its companions, and the coupling grows. The force strengthens. The gluon field becomes more intense, more self-reinforcing, more confining. At the distances characteristic of a proton's size, roughly 1 femtometer, the coupling is enormous. The quarks are bound with tremendous force. They're trapped. So the gluon's color charge creates 2 complementary phenomena that together define the character of the strong force. At short distances, anti-screening by virtual gluons weakens the effective coupling, giving quarks a semblance of freedom. At long distances, the same anti-screening strengthens the coupling beyond all measure, making confinement inescapable. And here's something remarkable about this. It means that the very feature that makes gluons effective at carrying the strong force, their color charge, is the same feature that makes the force confining. The force carrier's charge is both the mechanism and the prison. The gluon does its job precisely because it carries color, and it can never escape precisely because it carries color. These aren't separate properties, they're two consequences of the same underlying fact. Now contrast this once more with electromagnetism to see how profound the difference is. In electromagnetism, the photon has no charge, so it doesn't contribute to the running of the coupling in the anti-screening direction. The coupling only increases at shorter distances due to screening by virtual electron-positron pairs. There's no mechanism to strengthen the force at longer distances, so electromagnetism never confines. You can always pull two charges apart if you have enough energy. At sufficient separation, the force between them becomes negligible. This is why free electrons exist. This is why you can ionize atoms. This is why charged particles roam freely through the universe. In the strong force, you can never pull quarks apart. You can never isolate a gluon. The force doesn't let go. And the reason is that the force carrier itself is part of the problem. The messenger is entangled with the message in a way that creates a feedback loop with no exit. There's a beautiful way to visualize this difference. Think about the field lines between two charged particles. In electromagnetism, the field lines fan outward from one charge to the other, spreading through space like the fibers of a stretched cotton ball. The lines disperse, they fill a wide volume, and because they're spread thin, the field is weak at any given point far from the charges. In the strong force, the field lines don't fan out. The gluons carrying those field lines are themselves color charged, and they attract each other. The field lines pull together, they collapse inward. Instead of a diffuse cloud of field filling the space between two quarks, the field condenses into a narrow tube, a tight string-like structure connecting the quarks. All the field energy is concentrated in this tube, rather than spread through the surrounding volume. This flux tube has real physical properties. It has a roughly constant energy per unit length, often quoted as approximately 1 giga-electron-volt per femtometer, which works out to about 14 metric tons of force. That's the tension in the tube connecting two quarks inside a proton. 14 tons of pulling force generated by a structure smaller than an atomic nucleus. It's an extraordinary amount of energy packed into an inconceivably tiny space. And because the energy per unit length is constant, the total energy stored in the tube increases linearly with its length. Pull the quarks apart and the tube stretches. The energy goes up in direct proportion to the distance. This is fundamentally different from electromagnetism, where the energy stored in the field decreases as charges separate. In QCD, the energy increases. Stretching the tube costs energy. More and more energy, without limit. This is what confinement looks like at the level of field dynamics. The gluon field between quarks forms a self-reinforcing tube that stores more and more energy as quarks are separated. There's no way to reduce this energy except by bringing the quarks back together. The tube doesn't dissipate. It doesn't spread out. It holds its shape because the gluons in the tube attract each other and keep the field compressed. The self-interaction of the gluon field is what maintains the tube's integrity. Compare this to what would happen if you tried to separate two magnets. Pull them apart, and the magnetic field between them weakens. Beyond a certain distance, you barely feel the attraction. You can separate them completely, and each magnet continues to exist independently. The field between them diminishes to nothing. Try the same thing with two quarks, and the field between them doesn't diminish. It concentrates, it intensifies. The tube connecting them becomes a taut cable of confined gluon field, resisting your effort with ever-increasing energy. The harder you pull, the more energy you dump into the tube, and that energy cannot escape because the gluons in the tube are themselves color-charged and therefore confined. There's another remarkable feature of gluon self-interaction that deserves attention. In electromagnetism, the interactions between force carriers are absent at the simplest level. Photons don't directly interact with each other. There's no vertex in the theory where 3 photons meet, or 4 photons meet. The simplest Feynman diagrams for photon-photon scattering involve loops of virtual electrons, making the process extremely rare and feeble. It's so weak that direct photon-photon scattering wasn't experimentally confirmed until 2017, using the intense electromagnetic fields produced in lead-lead collisions at the Large Hadron Collider. In QCD, gluon self-interaction is not some subtle correction. It's the dominant feature of the theory. There are vertices in QCD where 3 gluons meet directly. There are vertices where 4 gluons meet directly. These are fundamental interactions built into the basic structure of the theory, not rare quantum corrections. They happen constantly, at leading order, in every single strong force interaction. The 3-gluon vertex is particularly important. It means a single gluon can split into 2 gluons, or 2 gluons can merge into 1. This happens all the time inside hadrons. Gluons are constantly splitting, merging, being emitted and absorbed. The interior of a proton is a turbulent dynamical system where the gluon field is in constant flux, reshaping itself moment to moment. The 4-gluon vertex is equally fundamental. 4 gluons can all interact at a single point in spacetime. This means gluon-gluon scattering is a basic tree-level process in QCD, not a rare loop-level correction as photon-photon scattering is in electromagnetism. Gluons scatter off each other readily and frequently. Inside a proton, gluons are colliding with each other all the time. These self-interactions create a feedback loop. Gluons generate more gluons. Those new gluons generate still more gluons. The gluon field is self-amplifying. If you try to add energy to the system, much of that energy goes into creating more gluons, rather than accelerating existing particles. If you try to remove a gluon from the system, the field reorganizes, generating new gluons to fill the gap. The system resists perturbation with an almost organic tenacity, maintaining its structure through constant self-renewal. This is also why the mathematical description of the strong force is so much more difficult than electromagnetism. In electromagnetism, because photons don't interact with each other, the theory is linear to a good approximation. You can solve many problems exactly. The hydrogen atom, for instance, can be solved analytically. You get precise energy levels that match experimental measurements to extraordinary accuracy. In QCD, the self-interaction of gluons makes the theory fundamentally nonlinear. Exact solutions are almost impossible. The standard technique in quantum field theory is perturbation theory, where you calculate approximate answers by starting with the simplest interaction and adding corrections from more complex processes. In electromagnetism, this works beautifully because the coupling constant is small, about 1/137. Each correction is much smaller than the previous one, so the series converges quickly. In QCD at low energies, at the energy scales relevant to proton structure, the coupling constant is large, close to 1, or even bigger. Perturbation theory fails catastrophically. Each correction is as big as or bigger than the previous one. The series doesn't converge. You can't calculate anything reliable this way. This is why understanding the proton's internal structure, why understanding confinement, is so difficult. The mathematical tools that work for electromagnetism simply don't work here. Physicists have developed a different approach, called lattice QCD, to handle this regime. Instead of working with continuous spacetime, they approximate spacetime as a discrete grid, a lattice of points. They place quarks on the lattice points and gluons on the connections between points, and then use powerful supercomputers to calculate the behavior of the system. This approach doesn't rely on perturbation theory. It can handle the strong coupling regime where confinement occurs. Lattice QCD calculations have been enormously successful. They've calculated the masses of protons and neutrons from first principles, starting with just the quark masses and the strong coupling constant, and getting results that match experimental measurements to within a few percent. They've confirmed that the flux tube picture of confinement is correct, directly observing the formation of string-like color field tubes between separated quarks on the lattice. They've calculated the properties of numerous hadrons and matched experimental data across a wide range of phenomena. These computational successes provide strong evidence that QCD, with its self-interacting gluons and color confinement, is the correct theory of the strong force. The theory works, it matches experiment, and it does so precisely because of the features that make it so different from electromagnetism. The gluon's color charge, the self-interaction, the nonlinear field dynamics, the flux tubes, the confinement. All of these are not bugs in the theory, they're features. They're exactly what's needed to explain the observed behavior of the strong force. So when we ask what makes the gluon special, the answer is its charge. The gluon carries the very charge it mediates. This single property transforms the strong force from something that might have resembled electromagnetism into something completely different. A force that confines rather than releases. A force that strengthens with distance rather than weakening. A force whose carriers are permanently trapped inside the particles they hold together. The gluon's color charge is the key to everything. It makes the strong force self-interacting. Self-interaction creates anti-screening. Anti-screening creates asymptotic freedom at short distances and growing coupling at long distances. Growing coupling creates flux tubes. Flux tubes store energy proportional to their length, and that stored energy makes it impossible to ever extract a quark or gluon from a hadron. One property of the gluon, its color charge, creates a chain of consequences that reshapes the entire structure of matter. The photon, by contrast, is electrically neutral, and electromagnetism is gentle, linear, and allows free charged particles to roam the universe. The gluon is color charged, and the strong force is fierce, non-linear, and locks its constituents away forever. Two force carriers, two charges, two completely different physics. And the difference comes down to one question: does the messenger carry the message's charge? For photons, the answer is no. For gluons, the answer is yes. And that single yes changes everything. So now we understand the essential difference. Photons are neutral, gluons are charged. And that difference transforms everything about how the strong force behaves. But understanding the principle is one thing. Understanding what it actually does to matter, what it means in practice when you try to pull quarks apart, is something else entirely. Because confinement isn't just a theoretical prediction written on a chalkboard. It's a physical process. It has stages. It has consequences. And those consequences are so strange that when physicists first began to understand them, it challenged everything they thought they knew about how forces work. Let's set up a thought experiment. Imagine you could reach inside a proton and grab hold of one of its quarks. Just pinch it between your fingers and start pulling. What would happen? At first, when the quark is still very close to its companions, you wouldn't feel much resistance. This is asymptotic freedom at work. At very short distances, the strong coupling is relatively weak. The quarks are almost free. You might think, for a brief, misleading moment, that pulling a quark out of a proton is going to be easy. But as you pull the quark even a tiny distance away from the other two, things change rapidly. The color field between your quark and the remaining pair begins to organize itself. Remember, the gluons carrying this field attract each other because they carry color. And the tube stores about 2 giga-electron-volts. 3 femtometers, 3 giga-electron-volts. The energy just keeps climbing, linearly, with no end in sight. This is the linear confining potential, and it's completely unlike anything in electromagnetism. If you pull 2 electrically charged particles apart, the energy stored in the electric field between them actually approaches a finite value. There's a maximum amount of energy stored in the system, related to the charges and the initial separation. At infinite distance, the energy reaches a plateau. The charges become independent. They stop interacting. In the strong force, there is no plateau. The energy never levels off. It keeps rising as long as you keep pulling. To separate a quark to infinity would require infinite energy, and infinite energy doesn't exist in any finite region of the universe. So the separation can never be completed. The quark can never be freed. Not because we lack the technology, not because our accelerators aren't powerful enough, but because the laws of physics don't permit it. The energy required is literally infinite. But wait, if the energy keeps increasing as you pull, and you're pumping more and more energy into the system by doing work against this enormous force, where does all that energy go? You might imagine the flux tube just getting longer and longer, storing more and more energy, stretching across the laboratory like an impossibly thin rubber band. But that's not what happens. Something far more dramatic occurs. As the energy stored in the flux tube increases, there comes a point where the energy density in the tube is sufficient to create new matter. Remember Einstein's famous equation, energy and mass are equivalent. If you concentrate enough energy in a small region, that energy can convert into particles. Specifically, when the energy in the flux tube reaches a threshold, the tube can create a quark-antiquark pair from the vacuum. This is called string breaking, and it's one of the most remarkable phenomena in all of particle physics. Here's how it works. You're pulling your quark away from the proton. The flux tube stretches, storing more and more energy. When the energy in the tube reaches roughly the mass energy of a quark-antiquark pair, around 600 to 700 mega-electron-volts for light quarks, like up and down quarks, the vacuum itself tears open. A new quark and a new antiquark materialize inside the tube. They don't come from anywhere, they're created from the energy stored in the gluon field, conjured from the vacuum by the intense colour field inside the tube. Think about what's happening at that moment. The flux tube is a region of space filled with concentrated gluon field energy. The energy density is enormous, comparable to conditions inside a neutron star. And energy, as Einstein showed, is interchangeable with mass. When enough energy accumulates in a small enough region, the vacuum becomes unstable. It's cheaper, energetically, for the vacuum to produce a quark-antiquark pair than for the flux tube to keep stretching. So the vacuum does what physics always does. It finds the lowest energy state available, and that means creating new matter. The pair doesn't materialize at one specific point like a light bulb switching on. The process is quantum mechanical. The quark and antiquark emerge from the vacuum at some location along the tube, typically near the middle where the energy density has been building longest. They appear already carrying color charge, already interacting with the gluon field, already being pulled toward the separated quarks at either end of the tube. The moment they materialize, they begin to change the topology of the entire system. But here's the crucial detail. The new quark and antiquark don't appear randomly. They appear in a way that neutralizes the color charge. The new antiquark attaches to the quark you were pulling, forming a meson, a color-neutral particle. The new quark attaches to the remaining pair of quarks you left behind, restoring them to a color-neutral baryon. The flux tube between them snaps. The tension vanishes, and instead of one proton with a quark being dragged out, you now have a proton and a meson sitting side by side. Two complete color-neutral particles. You didn't free a quark, you created new particles. This is what happens every single time you try to extract a quark or gluon from a hadron. No matter how much energy you invest, no matter how hard you pull, the result is always the same. New particles are created. The color charge is neutralized. Confinement is maintained. It's as if you try to pull one end of a magnet away from the other, and instead of getting an isolated north pole and an isolated south pole, the magnet broke in half, and each half immediately grew a new opposite pole. You'd end up with two complete magnets instead of two isolated poles. Actually, with magnets, this analogy is only approximately true. Magnetic monopoles might exist in principle, even if none have been found. But for color charge, confinement appears to be absolute. There is no known mechanism by which a color-charged particle can exist freely. The universe simply doesn't permit it. Let's think about this from the energy perspective to make sure the picture is clear. You start with a proton at rest. Its mass energy is about 938 mega-electron-volts. You begin pulling a quark. The system's energy increases as the flux tube stretches. When the energy reaches the threshold for pair creation, perhaps around 1300 to 1400 mega-electron-volts total, the tube snaps. You now have a proton at roughly 938 mega-electron-volts and a pion at roughly 140 mega-electron-volts, plus some kinetic energy. The total energy is accounted for. Energy is conserved perfectly. But the topology of the system has changed. One hadron has become two hadrons. One flux tube has become two shorter flux tubes inside two separate color-neutral particles. No free color charge anywhere. And if you pump in even more energy, if you pull harder, invest thousands or millions of electron volts, the tube doesn't produce just one quark-antiquark pair, it produces several, or many. The enormous energy cascades into a shower of new particles. Multiple mesons, baryons and antibaryons spray outward, each one individually color-neutral, each one confining its quarks and gluons safely inside. The more energy you invest in trying to free a quark, the more new particles you create. You're literally manufacturing matter from your effort to overcome confinement, and confinement wins every single time. This is exactly what we observe in particle accelerators. When protons collide at high energies in the Large Hadron Collider, for instance, the quarks and gluons inside the protons interact violently. Enormous amounts of energy are concentrated in tiny regions. Quarks are knocked sideways at tremendous speeds. Gluons are radiated with enormous energies. For a fleeting instant, individual quarks and gluons are flying apart from each other, but they never escape. As each quark or gluon flies outward from the collision point, it stretches a flux tube behind it. The tube stores energy. The energy reaches the pair creation threshold. New quarks and antiquarks materialize. They combine into hadrons. More flux tubes stretch. More pairs are created. More hadrons form. The result is a collimated spray of hadrons, all moving in roughly the same direction as the original quark or gluon. This spray is called a jet. Jets are one of the most dramatic and visually striking phenomena in particle physics. In detector images from the Large Hadron Collider, you can see them clearly. Narrow cones of particles spraying outward from the collision point, sometimes with enormous energy. A single jet might contain dozens or hundreds of individual hadrons, mostly pions, but also kaons, protons, neutrons, and other particles, all flying in roughly the same direction, all tracing back to a single quark or gluon that was knocked out of the collision. The jet structure directly reflects confinement. Each jet corresponds to a single color-charged parton, either a quark or a gluon, that was produced in the hard collision. That parton couldn't travel freely through space because it carries color charge. Instead, it produced a cascade of new particles through flux tube breaking, a process physicists call hadronization or fragmentation. The jet is the observable fingerprint of a parton that tried to escape, but was caught by confinement and converted into a spray of color-neutral hadrons. This is worth emphasizing. We can't see individual quarks or gluons in a detector. What we see are jets, but the properties of those jets, their energy, their direction, their internal structure, tell us precisely what parton created them. We can measure the momentum of a gluon by measuring the jet it produces. We can determine whether it was a quark or a gluon based on the jet's characteristics. Gluon jets, for instance, tend to be broader and contain more particles than quark jets, because gluons carry more color charge and radiate more strongly. The 1979 discovery at the Petra Collider in Hamburg that we mentioned earlier was precisely this kind of observation. When electrons and positrons annihilated at high energy, they could produce a quark-antiquark pair flying apart in opposite directions. Each quark would produce a jet, so the typical event had two jets pointing in opposite directions, but sometimes the quark or antiquark would radiate a high-energy gluon before hadronizing. That gluon would produce its own jet, 3 jets. The third jet was the gluon's signature. By measuring the properties of these 3 jet events, angles, energies, and particle multiplicities, physicists confirmed that the third jet matched the theoretical predictions for a spin-1 color-charged particle, a gluon. It was the first direct evidence that gluons exist. Since then, jet physics has become one of the precision tools of particle physics. Experimentalists measure jet properties with extraordinary accuracy and compare them to QCD predictions. The agreement is remarkable, confirming the theory at a level of precision that leaves essentially no doubt that QCD is correct. But let's come back to the physical picture of confinement and probe it more deeply, because there's something philosophically profound about what's happening here. When we say quarks and gluons are confined, we're saying something extraordinary about the relationship between energy and matter. In most areas of physics, energy and matter are related but distinguishable. You can have a particle at rest, possessing mass energy but no kinetic energy. You can add energy by accelerating it. You can remove energy by decelerating it. Energy is something a particle has. It's a property of the particle, not the particle itself. But in confinement, the boundary between energy and matter dissolves. The energy stored in the gluon field, in the flux tube stretching between quarks, is not just energy, it's potential matter. It will become matter the moment the field is stretched far enough. The gluon field energy converts directly into quark-antiquark pairs, into new hadrons, into observable particles with mass and momentum. The field itself is a reservoir of potential particles waiting to be born. This means the gluon field inside a proton is not just a force, it's a substance. It has energy, it has structure, it has the capacity to create matter. In a very real sense, the gluon field is what gives the proton most of its mass. We'll explore this in more detail later, but for now, note that the quarks inside a proton, the up and down quarks, have masses of only a few mega-electron-volts each. 2 up quarks and 1 down quark together contribute only about 9 mega-electron-volts of mass. The proton's total mass is about 938 mega-electron-volts. Where does the rest come from? From the gluon field, from the energy of the strong interactions inside the proton, from confinement itself. The mass you feel when you pick up an object, the weight that presses you into your chair, almost all of it comes from the energy of confined gluon fields inside protons and neutrons, not from the quarks themselves. Let's also discuss something that might seem paradoxical. If confinement is absolute, if we can never isolate a quark or gluon, how can we be sure they're real? How do we know the interior of a proton is genuinely made of quarks and gluons, rather than being some smooth, featureless blob? The answer comes from multiple independent lines of evidence that all converge on the same picture. First, deep inelastic scattering. When high-energy electrons or neutrinos are fired at protons, the scattering pattern reveals that the protons have internal structure. The cross-sections, the probabilities of scattering at various angles and energies, match what you'd expect if the proton contained point-like constituents with specific charges and spins. The measurements are consistent with 3 quarks carrying fractional electric charges of plus 2/3 and minus 1/3, exactly as the quark model predicts. These measurements also reveal that quarks carry only about half the proton's momentum. The rest is carried by electrically neutral objects inside the proton that don't interact with the electron probe. Those neutral objects are gluons. Second, jet production. As we discussed, high-energy collisions produce jets whose properties match QCD predictions for quarks and gluons with specific color charges, spins, and interaction strengths. The angular distributions of jets, their energy spectra, their multiplicity patterns, all match the theory. The 3 jet events at Petra confirmed the gluon's existence. Modern measurements at the LHC have mapped out gluon properties in exquisite detail. Third, lattice QCD calculations. Supercomputer simulations of QCD on a space-time lattice reproduce the observed spectrum of hadrons, the masses of protons and neutrons, the properties of pions and kaons, and dozens of other quantities, all starting from the fundamental QCD Lagrangian with its quarks and gluons. If the theory's basic ingredients were wrong, these calculations wouldn't work. The fact that they match experiment to within a few percent confirms that quarks and gluons are the right degrees of freedom. Fourth, the running of the strong coupling constant. Measurements at different energy scales show that the effective strength of the strong force changes with energy exactly as QCD predicts, decreasing at high energies, consistent with asymptotic freedom, and increasing at low energies, consistent with confinement. This running has been measured across a vast range of energies, from a few giga-electron volts to several tera-electron volts, and the data matches the QCD prediction with extraordinary precision. The measured values of the strong coupling constant at different energies all converge when evolved to a common reference scale, confirming that a single underlying theory describes the strong force across all these scales. Fifth, the quark-gluon plasma. At extremely high temperatures and densities, QCD predicts that confinement should break down. The hadrons should melt. Quarks and gluons should become deconfined, forming a new state of matter called the quark-gluon plasma. This state of matter existed in the early universe, during the first few microseconds after the Big Bang, when temperatures were above roughly 2 trillion degrees. It has also been recreated in laboratory experiments at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory and at the Large Hadron Collider at CERN by smashing heavy nuclei like gold or lead together at nearly the speed of light. These collisions produce tiny fireballs with temperatures exceeding 4 trillion degrees, hot enough to deconfine quarks and gluons for a fleeting instant. The fireball exists for only about 10 to the minus 23 seconds before cooling and reconfining into a shower of hadrons. But during its brief existence, the matter inside behaves like nothing else we've ever encountered. It behaves like a nearly perfect liquid. This was one of the biggest surprises in modern physics. Physicists expected the quark-gluon plasma to behave like a gas, with quarks and gluons bouncing around freely like molecules in a hot vapor. After all, deconfinement was supposed to set the quarks and gluons free. They should have been flying around independently, barely interacting, in the asymptotically free regime. Instead, the plasma behaves as a liquid with almost zero viscosity. It flows with less internal friction than any known substance. Superfluid helium, the coldest and most frictionless liquid we can produce in a laboratory, still has more viscosity than the quark-gluon plasma appears to have. The plasma is the most perfect liquid ever observed. It flows as a collective whole, with quarks and gluons moving in coordinated patterns rather than flying around independently. This means that even when confinement breaks down, even when individual hadrons dissolve, the strong force still binds the quarks and gluons into a collective state. They're not truly free. They're deconfined from individual protons and neutrons, yes, but they're still interacting intensely with each other, still bound into a dense, strongly coupled medium. The strong force doesn't simply switch off above the deconfinement temperature. It changes character, releasing quarks from individual hadrons, but immediately binding them into something else, a hot, dense, astonishingly fluid collective. The observations at these facilities match QCD predictions for the quark-gluon plasma. The particle yields, the flow patterns, the correlations between particles, all are consistent with a state of deconfined quarks and gluons briefly existing before reconfining. This is strong evidence that confinement is a phase of QCD, not an absolute eternal property. At sufficiently extreme conditions, confinement can be overcome, but only by creating conditions so extreme that the entire concept of individual hadrons breaks down. You don't free individual quarks, you create a new state of matter entirely, a soup of quarks and gluons all mixed together, none of them individually free, all of them interacting intensely with each other. And the moment conditions cool below the critical temperature, confinement reasserts itself and hadrons reform. This is deeply telling. Even when you push the system to the absolute extreme, even when you recreate conditions that existed only in the first moments after the Big Bang, you still don't get free quarks or gluons. You get a collective state where quarks and gluons are deconfined from individual hadrons, but still confined to the plasma itself. And the moment you stop supplying the extreme energy, confinement returns. It's as if the universe has a deep, unshakable commitment to keeping color charge locked away, using every mechanism at its disposal to ensure that no isolated color-charged particle ever exists in the cold, ordinary vacuum. There's something almost willful about it. The universe doesn't just make confinement possible, it makes it mandatory. It builds the requirement into the fundamental structure of the force through the gluon's color charge, through the self-interaction of the gluon field, through the formation of flux tubes, through the mechanism of string breaking and pair creation. Layer after layer of physical processes, all conspiring to enforce the same rule. No free color charge, ever. The strength of this enforcement is remarkable. We've probed matter at the highest energies achievable on Earth. We've recreated the conditions of the early universe in laboratory collisions. We've searched for free quarks in cosmic rays, in bulk matter, in the oceans, in moon rocks brought back by Apollo missions. Nobody has ever found a free quark. Nobody has ever found a free gluon. The experimental upper limits on the existence of free fractional charges in ordinary matter are extraordinary. Less than one free quark per roughly 10 to the 20 nucleons. Confinement is, as far as any experiment has ever shown, perfect. And yet, despite all this evidence, despite the overwhelming success of QCD, despite the lattice calculations and the jet measurements and the quark-gluon plasma observations, there's something we still don't fully understand. We don't have a rigorous mathematical proof that QCD actually produces confinement. This might surprise you. We have a theory. We have enormous evidence that the theory is correct. We can calculate its predictions using supercomputers, and they match experiment. But we lack a clean, analytic, mathematical proof that starting from the QCD equations, confinement necessarily follows. This is one of the most famous unsolved problems in mathematical physics. It's one of the 7 Millennium Prize problems identified by the Clay Mathematics Institute in the year 2000. The prize offers $1 million for a rigorous proof that the quantum Yang-Mills theory, the mathematical framework underlying QCD, has a mass gap. A mass gap means the lightest particle in the theory has a non-zero mass. This is related to confinement, because in a confining theory, all physical particles are massive hadrons, not massless gluons. Proving the mass gap would essentially prove that confinement is a mathematical consequence of the theory, not just an observed phenomenon that we verify numerically. Nobody has claimed this prize, despite over 50 years of effort by some of the most brilliant mathematical physicists in the world. The proof remains elusive. We know from lattice calculations that confinement occurs in QCD. We verified it computationally to extraordinary precision, but we can't prove it analytically. The mathematical structure of non-abelian gauge theories in 4 spacetime dimensions is simply too complex for current mathematical techniques. This is humbling. It reminds us that even in physics, where our theories are spectacularly successful and our experimental confirmations are overwhelming, there are still deep mathematical questions we can't answer. QCD is the theory of the strong force. It works, it matches every experiment, but we can't fully prove why it works from first principles. The gluon's self-interaction, which is the root cause of confinement, creates mathematical complexity that exceeds our current ability to analyze rigorously. Some partial results exist. In simplified versions of QCD, with fewer dimensions or different gauge groups, confinement has been proven. In certain supersymmetric extensions of Yang-Mills theory, which have additional mathematical symmetry, exact results related to confinement have been obtained. These provide evidence that confinement is a generic feature of non-abelian gauge theories, not a peculiarity of the specific version we find in nature. But the full proof for realistic QCD in 4 dimensions remains open. So confinement stands as one of the most experimentally confirmed, yet mathematically unproven phenomena in all of science. We see it everywhere. Every proton and neutron in the universe is a testament to it. Every collision at the LHC confirms it. Every lattice calculation reproduces it. The physical evidence is as strong as evidence gets, but the mathematical proof is missing. The gluon's color charge, the self-interaction, the flux tubes, the string breaking, the jets, the quark-gluon plasma. All of this forms a coherent, consistent, abundantly confirmed picture. We understand the mechanism. We understand why confinement happens in physical terms. The gluons carry color charge, so the field self-interacts, so the field lines collapse into tubes, so the energy grows linearly with distance, so pair creation occurs before a quark can be freed. Each step follows logically and physically from the previous one. The chain of reasoning is clear. The experimental evidence at every stage is strong. But translating all of this into rigorous mathematics, proving that the QCD equations necessarily produce a confining vacuum state with a mass gap, remains beyond our reach, for now. What we can say with confidence is this: confinement is real. It's a physical phenomenon observed in every experiment that probes the strong force. It's a consequence of the gluon's color charge and the resulting self-interaction of the gluon field. It shapes the structure of all ordinary matter in the universe, and it ensures that gluons, the particles responsible for holding atomic nuclei together, can never be observed in isolation. They exist inside every proton and neutron. They carry roughly half the momentum of every nucleon. They're responsible for the vast majority of the mass of everything you can touch and feel, and yet they are permanently, irrevocably hidden from direct view, sealed inside hadrons by a force they themselves generate and maintain.
So we've established that gluons carry color charge, that this makes the strong force self-interacting, and that self-interaction leads to confinement. No free quarks, no free gluons, ever. But now let's turn inward. Let's look at what gluons actually do inside the particles they're trapped in, because the interior of a proton is one of the most extraordinary environments in all of physics. And what gluons do in there is far more important than most people realize. In fact, gluons are responsible for something you experience every moment of your life without ever knowing it. They're responsible for almost all of your mass. Let me explain. You have a body. That body has mass. You step on a scale and it reads some number in kilograms or pounds. That mass comes from the atoms in your body. The atoms get their mass almost entirely from their nuclei, since electrons contribute less than 1/20%. And the nuclei get their mass from the protons and neutrons they contain. So your mass, the mass of everything you've ever touched, lifted, pushed, or carried, ultimately comes from protons and neutrons. If you understand where the proton gets its mass, you understand where virtually all mass in the everyday world comes from. A proton is made of 2 up quarks and 1 down quark. The up quark has a mass of about 2.2 megaelectronvolts. The down quark has a mass of about 4.7 megaelectronvolts. Add them up. 2 up quarks at 2.2 each gives 4.4. 1 down quark at 4.7 gives 4.7. Total quark mass inside a proton is about 9.1 megaelectronvolts. The proton's measured mass is 938.3 megaelectronvolts. The quarks contribute less than 1% of the proton's mass. Less than 1%. The remaining 99% comes from somewhere else. It comes from the energy of the strong force itself. It comes from gluons and from the dynamics of the confined color field. This is one of the most profound consequences of Einstein's equivalence of mass and energy. The energy stored in the gluon field inside the proton, the kinetic energy of quarks buzzing around at nearly the speed of light, the energy of virtual quark-antiquark pairs constantly appearing and disappearing, all of this energy contributes to the proton's mass. When you step on a scale, you're overwhelmingly weighing the energy of quantum chromodynamics. You're weighing gluon field energy. You're weighing confinement itself. Let's look inside the proton more carefully. Because the naive picture of 3 quarks sitting quietly inside a bag, connected by gluon springs, is wildly misleading. The actual interior of a proton is nothing like that. It's a seething, turbulent, fantastically dynamic environment where gluons dominate. Physicists have mapped the interior of the proton using deep, inelastic scattering experiments, colliding high-energy electrons, muons and neutrinos with protons and measuring what comes out. These experiments don't photograph the inside of the proton directly. Instead, they measure what fraction of the proton's total momentum is carried by each type of constituent at different resolution scales. The results are encoded in mathematical functions called parton distribution functions, which tell you the probability of finding a particular type of parton, quark or gluon, carrying a given fraction of the proton's momentum. The results are striking. At moderate resolution scales, the kind probed by experiments at energies of a few giga-electron volts, the proton's momentum is shared roughly equally between quarks and gluons. About half the momentum is carried by quarks and about half by gluons. But as you increase the resolution, probing at shorter distances and higher energies, you see more and more gluons. At the energy scales reached by the Large Hadron Collider, gluons carry the dominant share of the proton's momentum. There are far more gluons inside a proton than quarks, and these aren't just a few extra gluons. At high resolution, the gluon distribution rises steeply at low momentum fractions. There's a vast population of low momentum gluons, a dense sea of color field fluctuations filling the proton's interior. If you could somehow take a snapshot of all the partons inside a proton at LHC resolution scales, you'd see 3 valence quarks, the 2 ups and 1 down that give the proton its quantum numbers, surrounded by an enormous cloud of gluons and virtual quark-antiquark pairs. The gluons vastly outnumber everything else. This gluon-dominated interior is not a static structure, it's constantly in motion. Gluons are being emitted and absorbed by quarks. Gluons are splitting into pairs of gluons. Pairs of gluons are merging into single gluons. Gluons are producing virtual quark-antiquark pairs that exist for a fleeting moment before annihilating back into gluons. The entire system is churning with quantum activity, reshaping itself trillions upon trillions of times per second. The proton is less like a solid object and more like a sustained quantum storm, a self-maintaining pattern of field energy confined by the dynamics of its own color charge. This picture has been confirmed with remarkable precision. Measurements from experiments at Hera, a large electron-proton collider that operated in Hamburg from 1992 to 2007, mapped the gluon distribution inside the proton across a wide range of momentum fractions and energy scales. The results matched QCD predictions with extraordinary accuracy, confirming that the theory correctly describes the gluon content of the proton. More recent measurements at the LHC, particularly from the ATLAS and CMS experiments, have extended these measurements to even higher energies and smaller momentum fractions, consistently matching QCD. But the gluon story is far from complete. One of the most important open questions concerns what happens when you probe the proton at even higher resolutions, at even smaller momentum fractions, where the gluon density keeps rising. As you look at lower and lower momentum fractions, the number of gluons you find keeps growing steeply. But this growth can't continue forever. At some point, gluons must start overlapping in space. When the density becomes high enough, gluons should begin to merge and recombine as fast as they're being produced, reaching a saturation point. This predicted state of matter is called the color glass condensate, a dense, saturated state of gluon fields, where the gluon occupation number is so high that the system behaves almost classically despite being fundamentally quantum mechanical. The color glass condensate, if it exists, would represent a universal state of matter that all hadrons and nuclei look like when probed at sufficiently high energies. It would be a glimpse of gluonic matter in its most extreme, most densely packed form. Confirming or ruling out the color glass condensate is one of the primary goals of the Electron-Ion Collider, or EIC, currently under construction at Brookhaven National Laboratory in New York. The EIC is specifically designed to probe gluon-dominated matter with unprecedented precision. It will collide high-energy electrons with protons and with heavy nuclei, mapping the gluon distributions inside both. Heavy nuclei are particularly interesting because their larger size means higher gluon densities at accessible energies, making saturation effects easier to detect. The EIC is expected to begin operations in the early 2030s, and when it does, it will open an entirely new window into the gluon structure of matter. It may finally answer the question of how the dense gluons see inside every proton organizes itself at the smallest scales. The sheer abundance of gluons inside the proton has practical consequences for high-energy physics. At the Large Hadron Collider, protons collide at energies of 13 tera-electron volts. But most of the interesting physics doesn't come from quark-quark collisions. It comes from gluon-gluon collisions. When two protons smash together at the LHC, it's overwhelmingly gluons inside one proton interacting with gluons inside the other proton that produce the most energetic and interesting events. The discovery of the Higgs boson in 2012 was primarily made through gluon-gluon fusion, a process where two gluons, one from each proton, fuse together and produce a Higgs boson through a virtual top quark loop. Without the abundant gluon content of the proton, this process wouldn't occur at a high enough rate to detect. The Higgs discovery, one of the most important achievements in the history of particle physics, was fundamentally a gluon story. Now let's return to the question of mass, because the details are fascinating and they reveal something deep about the nature of matter itself. The proton's mass of 938 mega-electron-volts comes from several sources, and disentangling them requires both theoretical insight and computational power. The first contribution is the quark masses themselves. As we said, this is only about 9 mega-electron-volts, a tiny fraction. But this isn't the whole story for the quarks, because the quarks inside a proton aren't sitting still. They're confined to a region about 1 femtometer across, and the uncertainty principle demands that a particle confined to such a small region must have a large momentum. The quarks are zooming around inside the proton at speeds close to the speed of light. This kinetic energy contributes to the proton's mass. The second contribution is the gluon field energy. The gluons inside the proton carry energy, both kinetic energy from their motion and potential energy from their interactions. This is the dominant contribution to the proton's mass. The self-interacting gluon field, constantly fluctuating and reorganizing itself, contains an enormous amount of energy per unit volume. This energy, through the equivalence of mass and energy, manifests as mass. The third contribution comes from the trace anomaly, a subtle quantum effect with no classical analog. In classical physics, the strong force is scale invariant, meaning the theory looks the same at all distant scales. But quantization breaks this symmetry. The running of the coupling constant, asymptotic freedom, is itself a manifestation of this broken scale invariance. The trace anomaly contributes to the proton's mass in a way that's directly related to the running of the strong coupling. It's a fundamentally quantum mechanical contribution to mass, arising from the breaking of a classical symmetry by quantum effects. Lattice QCD calculations have successfully decomposed the proton's mass into these contributions. A landmark calculation published in 2018 by the QCD collaboration determined that the quark condensate contributes about 9% of the proton's mass. The quark kinetic energy contributes about 32%, the gluon field energy contributes about 36%, and the trace anomaly contributes about 23%. The gluon-related contributions dominate, accounting for the majority of the proton's mass either directly through gluon field energy or indirectly through their role in the trace anomaly and in confining the quarks. This means that when you pick up a 1 kilogram object, roughly 900 grams of that mass comes from the energy of the strong force, from gluon fields and quantum chromodynamic effects inside protons and neutrons. Only about 10 grams comes from the intrinsic masses of quarks, the masses generated by the Higgs mechanism. The Higgs boson, for all its fame, is responsible for less than 2% of the mass of ordinary matter. The strong force, and specifically the gluon field, is responsible for the rest. This is a deeply counterintuitive result. Most popular science accounts of the Higgs boson describe it as giving particles their mass, and this is true in a fundamental sense. The Higgs mechanism generates the intrinsic masses of quarks and leptons. Without the Higgs, quarks would be massless, and the strong force would behave differently. But in terms of the mass you actually experience in your daily life, the mass of tables and chairs and planets and stars, the Higgs plays a minor role. The dominant source of everyday mass is the dynamics of confinement, the gluon field energy inside protons and neutrons, the strong force doing what it does. Now let's address the question that sits at the heart of this entire exploration. What is a gluon actually made of? The answer requires us to think carefully about what we mean by made of. In everyday life, when we ask what something is made of, we're asking about its components. A house is made of bricks, wood, and glass. A brick is made of clay minerals. Clay minerals are made of atoms. Atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks and gluons. But what are quarks and gluons made of? As far as our best theories and experiments can tell, they're not made of anything. They're fundamental. They have no internal structure that we've been able to detect, no subcomponents, no deeper layer of building blocks. When we say something is fundamental in physics, we mean it's one of the basic ingredients of reality, not a composite object built from smaller parts. But this deserves careful explanation. Saying a gluon is fundamental doesn't mean it's a tiny solid ball with no features. A gluon is an excitation of a quantum field. Specifically, it's a quantum of the gluon field, which is the field associated with the strong force. Just as a photon is a quantum of the electromagnetic field, a ripple in the electric and magnetic fields that pervades all of space, a gluon is a quantum of the color field, a ripple in the strong force field that pervades the interior of every hadron. Quantum fields are the deepest layer of reality in our current understanding of physics. The standard model of particle physics describes the universe in terms of quantum fields. There's an electron field pervading all of space. Where the electron field is excited, we see an electron. There's a photon field pervading all of space. Where it's excited, we see a photon. There are quark fields, 6 of them corresponding to the 6 flavors of quarks: up, down, charm, strange, top, and bottom. And there are gluon fields, 8 of them corresponding to the 8 types of gluons, though they're usually described collectively as a single field with 8 components. When we say a gluon exists inside a proton, we mean the gluon field inside the proton is excited. The field is rippling, fluctuating, carrying energy and momentum. These excitations are what we call gluons. They're not tiny objects sitting inside the proton like marbles in a bag. They're waves in a field, patterns of energy in the color field that fills the proton's interior. And here's something important. These excitations are not permanent, individual, countable objects the way marbles are. In quantum field theory, the number of gluons inside a proton is not a fixed quantity. It fluctuates constantly. At any given instant, if you could somehow freeze the proton and count its gluons, you'd get a particular number, but the next instant, the number would be different. Gluons are being created and destroyed constantly as the field fluctuates. The question of how many gluons are in a proton doesn't have a single definite answer. It depends on when you look and at what resolution you probe. This is deeply quantum mechanical. In quantum field theory, particles are not permanent fixtures. They're temporary excitations of fields. They appear and disappear according to quantum rules. The proton persists not because it contains specific, identifiable particles that last forever, but because the overall pattern of field excitation is stable. The energy is distributed across the gluon and quark fields in a self-sustaining configuration that maintains itself indefinitely. The individual excitations come and go. The pattern endures. So the gluon is not made of anything. It is a quantum of the color field. It's a fundamental excitation, one of the basic units of reality as described by quantum chromodynamics. It carries color charge, spin 1, and 0 rest mass, though this last point requires immediate qualification because it connects directly to confinement. A gluon has 0 rest mass. In the equations of QCD, the gluon field is massless, just as the photon field is massless in quantum electrodynamics. You might think this means gluons should behave like photons, traveling at the speed of light, streaming freely through space. And indeed, if gluons could exist as free particles, that's exactly what they'd do. They'd be massless particles traveling at light speed, just like photons. But gluons can't exist as free particles. They carry color charge and are therefore confined. A free massless gluon would carry color charge through space, violating confinement. The universe doesn't allow this. So the masslessness of the gluon is a theoretical property of the field, not a property you can ever observe directly. You'll never measure a gluon's mass because you'll never isolate one. The gluon's masslessness is built into the equations but hidden by confinement. This connects to one of the most intriguing hypothetical objects in QCD, the glue ball. If gluons interact with each other so strongly, if they carry color charge and can form flux tubes and emit and absorb each other, can gluons bind together without any quarks at all? Can you have a particle made entirely of gluons? Theoretically, yes. QCD predicts the existence of glue balls, particles composed entirely of gluons bound together by their mutual color interactions. These wouldn't contain any quarks. They'd be pure gluon states, lumps of self-interacting color field energy. Lattice QCD calculations predict a spectrum of glue balls with specific masses. The lightest glue ball is predicted to have a mass of about 1,600 to 1,700 mega-electron volts, with quantum numbers of spin zero and positive parity. Heavier glue balls with higher spins are also predicted, but finding glue balls experimentally has proven extremely difficult. The problem is that glue balls have the same quantum numbers as certain quark-antiquark states, called mesons. A glue ball with spin zero and positive parity looks, from the outside, very similar to certain mesons with the same quantum numbers. The states mix. A physical particle observed in a detector might be partly glue ball and partly meson, a quantum superposition of both. Disentangling the glue ball component from the meson component is fiendishly difficult. Several experimental candidates for glue balls exist. Particles like the F0 at 1500 mega-electron volts and the F0 at 1700 mega-electron volts have been studied extensively. Their properties don't quite match what you'd expect for simple quark-antiquark mesons, suggesting they might have significant glue ball content. But no particle has been definitively identified as a pure glue ball. The mixing between glue ball and meson states makes clean identification elusive. This is an active area of research. Experiments at facilities like BES3 in Beijing, which studies particles produced in the electron-positron collisions at energies in the glue ball mass range, are specifically searching for glue ball signatures. The planned PANDA experiment at the Facility for Antiproton and Ion Research in Germany will also search for glue balls using antiproton-proton annihilation, a process that should be particularly good at producing gluon-rich states. Finding a confirmed glue ball would be a landmark achievement. It would demonstrate that gluons can form bound states by themselves, that the self-interaction of the color field is strong enough to create stable configurations of pure gluon energy. It would be the ultimate demonstration that gluons, while unable to exist as free particles, can organize themselves into observable structures through their mutual interactions. Now let's address asymptotic freedom one final time, because it connects to a deep truth about how nature works at different scales. Asymptotic freedom was discovered in 1973 by David Gross, Frank Wilczek, and David Politzer. Their calculations showed that the strong coupling constant decreases at shorter distances and higher energies. This meant QCD was a consistent quantum field theory that could be tested using perturbation theory at high energies, where the coupling is small enough for perturbative calculations to be reliable. The discovery had immediate consequences. It explained the results of deep inelastic scattering experiments, which showed quarks behaving as nearly free particles at short distances. It established QCD as the correct theory of the strong force, replacing earlier models that couldn't account for both confinement and the near freedom of quarks at high energies. And it provided a calculational framework for making precise predictions about high-energy strong force processes. Predictions that have been confirmed by decades of experiments. But asymptotic freedom also revealed something philosophically striking about the strong force. The force that holds nuclei together, the force responsible for almost all the mass in the universe, is fundamentally a force of opposites. At short distances it's weak, at long distances it's strong. It frees you when you're close, and imprisons you when you're far. This is the reverse of every other force in nature. Gravity weakens with distance. Electromagnetism weakens with distance. Even the weak force, though short-ranged for different reasons related to the mass of its carriers, doesn't exhibit this inverted distance behavior. The strong force is the only force that gets stronger, as you try to move away from it. And this inversion is entirely due to the gluon's color charge. Without color charge force carriers, there would be no anti-screening. Without anti-screening, there would be no asymptotic freedom. Without asymptotic freedom, there would be no confinement. The whole extraordinary edifice of the strong force, from the near freedom of quarks at short distances to the absolute imprisonment of color charge at long distances, rests on one foundational property of the gluon. And so we arrive at the deepest answer to our opening question. What is a gluon, and why can't it exist alone? A gluon is a fundamental quantum of the color field. It's an excitation of one of the basic fields in the standard model of particle physics. It has no internal structure. It's not made of anything smaller. It carries spin 1, 0 rest mass and color charge. There are 8 types of gluons, each carrying different combinations of color and anti-color charge, corresponding to the 8 generators of the SU3 symmetry group. The gluon carries the strong force between quarks, binding them into protons, neutrons, and other hadrons. It's responsible for roughly half the momentum inside every proton and neutron. Through the energy of the gluon field and the dynamics of confinement, it's responsible for over 90% of the mass of all ordinary matter. Without gluons, protons wouldn't hold together, nuclei wouldn't exist, atoms wouldn't form, chemistry would be impossible, life would be impossible. The material universe as we know it exists because of gluons, and a gluon cannot exist alone because it carries color charge. This is not a technological limitation. It's not something we might overcome with better equipment or cleverer experiments. It's a fundamental consequence of the laws of physics. The gluon's color charge makes the strong force self-interacting. Self-interaction causes the gluon field to form confining flux tubes between color-charged objects. The energy in those flux tubes grows without bound as color charges are separated, and when the energy is large enough, new particles are created from the vacuum, neutralizing the color charge and preventing any color charge particle from ever escaping. The gluon is trapped by the very force it carries. It's a messenger that is subject to its own message, a carrier that is held by the cargo it transports. Every gluon inside every proton inside every atom in your body is simultaneously doing its job and serving its sentence, carrying the force and being confined by it. It exists everywhere in ordinary matter. You couldn't exist without it. It generates most of your mass, holds your nuclei together, and makes the periodic table possible. And yet it is permanently hidden, locked behind the walls of confinement, invisible to any direct observation. There's something almost poetic about this arrangement. The most abundant force carrier inside ordinary matter, the particle most directly responsible for the mass and stability of the physical world, is the one particle we can never see. The one particle that can never be free. Photons stream across the universe, traveling billions of light years from distant galaxies to reach our telescopes. Gravitational waves ripple through space-time from colliding black holes and we detect them on Earth. Even neutrinos, ghostly and barely interacting, pass through the planet by the trillions every second, and we can catch a few in underground detectors. But gluons, the workhorses of ordinary matter, the particles doing the heavy lifting inside every atom, are permanently sealed away. You're built from confined gluon field energy. The chair beneath you is held together by gluon-mediated forces. The ground supporting the chair, the building supporting the ground, the planet supporting the building, all of it is gluon field energy given form by confinement. The night sky, every star visible to your eye, is powered by nuclear fusion, and nuclear fusion is possible only because gluons bind protons and neutrons tightly enough for them to fuse at stellar core temperatures. Every element heavier than hydrogen was forged in stars through processes that depend fundamentally on gluon-mediated nuclear binding. The carbon in your cells, the oxygen in your lungs, the iron in your blood, all of it was assembled in stellar furnaces held together by gluons, and not a single one of those gluons will ever be observed directly. Not one will ever fly freely through space. Not one will ever register as an independent particle in any detector. They exist. They are real. They are measured indirectly through jets and scattering and lattice calculations and 100 other methods, but they are confined, always confined, everywhere and forever. This is the gluon's paradox and its legacy. It is the most consequential invisible particle in physics, the most important thing you'll never see, the hidden architect of the material world. It builds everything and shows itself to nothing. It carries the strongest force in nature and is the ultimate prisoner of that force. It is fundamental, irreducible, and permanently caged. A particle